Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. Hi and welcome everyone. In this lesson or in this video, we will start talking about the scalar control of a distributed generator. In this lesson, we will learn how to use scalar control in order to control the active power and reactive power of a generator. So in this type or the scalar control, we are going to use a voltage control. And I will explain what does this mean, what does this even mean in this lesson. So let's start by remembering our system. So we said before that we have a connection with the point of common coupling, the point at which we are connecting our DG or static synchronous generator, the inverter in addition to our DC source. And by using control system, we can control how much active power and reactive power injected to the point of common coupling. Now, we can represent the system as we said before that the static synchronous generator at this point has a voltage V and angle phi, and VBCC at the point of common coupling, this point, and angle theta, right? Now, the question is, how can I control P and Q given to the grid? We said in the previous lesson, when we discussed synchronous generator, we said that by controlling the voltage, we can control Q, right? The reactive power. And by controlling delta, we can control active power. That is exactly what we are going to do for this system. Okay, so first we have this system, the DC source, and we have our inverter, which is consisting of group of switches, three-phase system, A, B, C, which is the output voltage for our system, and it has a group of upper switches and a group of lower switches. Okay, let's start. What's the first step? First step is that we control power. As we said before, that power is equal to VI over V of the generator itself multiplied by V BCC, voltage or point of common coupling, divided by X or the reactance between them, sine delta. So by controlling delta, we can control power. So what do we do exactly in control system? In control system, we use PI controllers. Why do we use PI controllers? Because PI controllers are used to take the error between the actual value and the reference value and bring it down to zero by controlling a certain quantity. So what we do exactly is that we would like a certain power from our DG. Okay, let's say for example 1 per unit, and our DG currently giving us 0.5 per unit. By taking the error between these two, it is given to a proportional integral controller, a PI controller. In reality, it can be a PI controller, it can be a sliding mode controller, it can be a super twisting sliding mode controller, it can be neural networks. There are many control techniques. Here I'm giving you an example for the most commonly used or the most well-known and simplest of all, the PI controller. So what does the PI controller do? It gives us an output signal that is used to bring this error down to zero. Okay, and as we said before that, what exactly control our power? We said delta, right? So the higher the error here, the more PI controller will give us more delta, the higher the delta needed, okay, in order to increase the power to reach the reference value of BDG. Okay, so that is the first part. However, if we remember that we are doing voltage control, which means I'm controlling V and angle phi. right? Let's get back here. The angle phi, this one, okay, right? So if we remember from the phasor diagram, we said that we have two vectors. We have this, like this, okay? We have V, which is our voltage here, and VBCC. Here we have angle theta. This angle is phi, and between them is delta. So what you can see here from this figure is that the angle that we need for our output voltage is equal to, or phi equal to, delta plus theta, right? So we have delta, which is given from the output of the BI controller, in addition to theta, which we need right now, which is the angle of the voltage of the point of common coupling. So how can we get theta? So we need delta plus theta, which is the phase of our three-phase system. We can do this using what we call a phase locked loop. And this one is responsible for synchronization with the grid. We will explain more about this later inside the course. But BLL is called the phase locked loop. What does it do? It takes the three-phase voltage VA, VB, VC of the grid. They are given to a phase locked loop. By measuring these three quantities, it can estimate the value of theta, or the angle of the voltage of point of common coupling, VBCC. Okay, so the output of the PLL will be theta, or the angle of the three phase. By adding these two angles together, we will get phi, which representing the angle of the output voltage of the three-phase inverter, right? Okay, so that is the first quantity. So we need angle. Now we need magnitude of the voltage, right? So we have angle from power. Now we need magnitude. The same concept here. You can see that power dependent on delta, difference between actual power and reference power and actual power to a PI controller gives us the required delta. Similarly, the difference between Q required of the DG and Q, which is given right now or taken right now, whatever the mode of operation, the difference between them, the error will be given to another BI controller that gives us the modulation index, which is the magnitude of voltage. Okay, how much is the voltage needed at the terminal of our friend, which is the inverter. Okay, so now we obtained amplitude and we obtained angle. Now taking these two values, we can represent it in a three-phase form. You will find that VA reference needed, VB reference, VC reference will be as follows. Three-phase signals, sine omega t minus 120, sine omega t plus 120. Three-phase shifted by 120 degrees, right? The phase angle of A, which is in B and C, is phi, which is given from here. And the amplitude of ABC is the modulation itself, which is dependent on the output of BI controller, which is dependent on the error between actual Q and the reference Q and the actual Q. Then we will have these three voltages, which we will need to control. We need to convert these three-phase voltages into pulses. These pulses are given to the switches of our inverter. So how can I actually do this? After getting the three-phase voltages, reference values, we use a comparator. What does the comparator do? It takes the required sine wave. Here we have sine wave, another sine wave, another sine wave, shifted by 120 degrees. We take these three signals and compare them with another signal. For example, we can compare it with a sawtooth, or we can compare it with a triangular wave. And by comparing these two, we can get the pulses that we need. For example, we will have, let's say for phase A, if you get back here, you will see that phase A has two switches, S1 and S4. Okay, for B, S3 and S6, S5 and S2 for C. Okay, each one has its own two switches, upper switch and lower switch. So if S1 equal to 1, then S4 will be the complementary, or the opposite of it will be 0. So if this switch is on, this one will be off. The reverse can happen too. If S4 is on, then S1 will be off. Okay, they are not operating at the same time. That's why you will find that the output of the comparator will be S1. If this one is 1, it means S1 is on. And we have here not gate, which means that S4 will be 0. It will be reversed. Similarly for B, which has the two switches, upper and lower, S3 and S4. And similarly for C, S5 and S2. Now, how does this technique actually works, or the generating of these pulses? I'm going to show you in the next lesson. Okay, so as you can see here, we have gate switches. Okay, what else? Now, as you can see here, again, let's summarize what I have just said. So we have all of our quantities together. So we have V, VBCC, the voltage, output voltage of this one, which is VA, VB, VC, the three-phase voltage. The magnitude itself is dependent on the reactive power needed. More reactive power, the higher the voltage needed, from the relations of reactive power in a synchronous machine, which we discussed in the previous lesson. So by doing this, we can control magnitude. For the angle, as you can see here, higher delta, more power given from generator to the grid. And the angle itself is summation of theta, which is obtained from the phase locked loop that we will discuss later, plus delta, which is obtained from this PI controller, dependent on the difference between these powers. Then we will have the three-phase output, which will be used as a comparator, our signal, which is called the modulating signal, VA star, VB star, VC star. All of this are modulating signals, which will be compared with a sawtooth or a triangular wave. And then we will have pulses like this. We will understand more in the next lesson. Thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy, or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You can join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes, and you can have them forever. And not only this, but any new courses that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits, you will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, light current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics.